So at any point that you guys want to go back and look over anything that we discussed, you have the opportunity to do that, and anybody else that's in the class will be able to look at it. So I think that's the neat thing about using this WIMBA classroom. Um, I've done it in the past where I've just done recordings and posted them, but since I would be taking the time to do it anyway, I thought it would be good to do it at a specific time and let people participate if they want to. So be sure if you have any questions or anything, you can either use your microphone and push the talk button to use your microphone and ask questions. You can indicate that you want to ask a question by raising your hand, and that will signify to me on the bar that you have a question or some other type of notification. Or you can type a question in the chat box, and I'll see that. So those are some ways to let me know if you need some clarification or have a specific question or anything like that. The first thing I wanted to mention is about the animations. There are a number of animations that are located in a couple of different areas if you want to use those in helping you learn some of the material. There are 2 folders in the Module 1 link, and so in each module there will be folders, at least 1 or more folders. I have them kind of broken down by topic. That'll have some animations in there. Some of them will be Shockwave files, which have a .swf extension. So you'll need a Shockwave plugin to be able to view those. Some of those are YouTube videos that you view online. Some of those have a .mov extension, so whatever software you use to view movies on your computer should be able to view those. So there's a couple of different formats that those are in. And then there's also some animations embedded in the PowerPoint. In order to view those, you have to be in an actual slideshow view of the PowerPoint, and you can click those. Some of them are just little activities to do, and then some of them are actually animations. So I do that so that there's enough different formats so that people will be able to view at least some of the animations. And you'll notice that some of the animations have kind of duplicated information in them because they do come from different sources. So ideally, in an ideal world, you'd be able to look at all of those and be able to pick out which ones you think are the most helpful or the most interesting for you to use to help you with the information. But since some of the information is duplicated, if you can view a couple of them, but you're unable to view others, you know that you're still getting some of the same information that's in some of the different animations. Some people are more visual learners. We're going to talk about learning styles probably next week in the course. And so the visual learners are going to like more of the animations and the figures, both in the PowerPoint and the book. Some people are more verbal or more comfortable with words. They're more comfortable with or more interested in learning from the book and from the text slides in the PowerPoint. So my goal is to try to give you enough different resources that you can use the ones that best fit with your learning style in trying to learn the material that we're looking at. So before we get started, are there any specific questions that anybody has that they want to ask? Marvin, go ahead. Did you have a question?
Yes, it's not necessarily a question. I believe I emailed you. There is a temporary problem receiving text books here at our community. So if you bear with me, I'll stay with that, but I'll keep with your modules in the meantime so I don't get behind if you take that into consideration.
Absolutely. There also a major issue with the textbook for my other class. So I've been running into that on a couple of different campuses with both of the classes that I'm teaching this summer. Most of what you need is in the PowerPoint. So if you use the PowerPoint and then whatever animations that you would like to use along with that, that's going to be the majority of the information that you'll need. You probably won't need your book as much until we get a little bit closer to maybe the first test, and that's a couple of weeks in. That's one of the reasons I wanted to do more of the discussion boards and the assignments. Those are things that you can use online resources for while you're waiting for your textbook. So I think that you'll be okay. If you run into specific problems or questions that you have, be sure and let me know. The information on the scientific method that's in the PowerPoint is probably going to be pretty helpful for you when you do the assignment. The other thing that you can do is the textbook publisher rents and sells chapters, individual chapters. So if you just wanted to get chapter 1 or you just wanted to get chapter 2, the website is cengagebrain.com. Let me see if I can put that up for you. That's the website for the publisher, and you can purchase or rent individual chapters or portions of the book. I'm not sure what the cost is on that, and since that's not going through a bookstore, that will not allow you to use financial aid. So there's some that's not going to necessarily be the ideal situation, but for anybody that's interested in doing ebooks or only getting certain parts of the book or trying to minimize costs, I have heard from students that's a little cheaper than buying the whole book through the bookstore if you're able to take that route. So, but I do recognize that there's some people that are still waiting on some texts. So I think that you'll be okay. And if you run into really specific challenges, let me know because I can work with people on that. Robin. Did you have a question? Okay, well, there's just some specific parts of the PowerPoint that I wanted to go through that I know are often confusing for students. So there's just some things that I wanted to kind of point out. The first thing that I kind of wanted to explain a little bit was about the levels of organization figure. That's one of the beginning figures in your chapter 1. So your textbook starts with this concept as one of the very first things that it points out, one of the very first things that it explains. And it illustrates this concept using this particular figure that's on page 5 of your text. And this actually is a pretty good roadmap for what the whole semester is going to be like for us. This is a pretty good outline of what our semester is gonna cover. So the figure starts with number 1, showing you atoms and atoms coming together to form molecules. It then talks about how molecules make up parts of cells, which is number 3, and they show you a cell there. It's actually showing you a nerve cell. And cells form different levels of organization inside organisms. So cells form tissues, tissues form organs, which form organ systems, which form the animals and plants that we know about. Organisms of the same type together form populations. So they're showing you a whole bunch of fish here. It's a population of fishes. And then communities are going to be all of the living organisms that grow together in a certain area. And then if you take both the organic and the inorganic matter that's there, that's going to form different ecosystems. And if you take all of the ecosystems together on the Earth, then you're going to have the biosphere. Biosphere is the most inclusive level, and it encompasses all of the regions of Earth. And so as we start this semester, we're going to study the structure of atoms and the structure of molecules. That's what we're going to look at in Chapter 2 this week. Chapter 3 gets into cell structure, and Chapter 4 gets into some cell functions. Then a little bit later in the semester, we're going to have a couple of weeks where we talk about organisms and how they work together to form populations. We're going to talk about communities and ecosystems. And then the very last week, we'll talk about the biosphere, how all of these communities and ecosystems fit together, but they're based on populations of organisms. And organisms are based on some of these functions and structures that are occurring inside of them. So since the class is an introduction to biology, we're going to be looking at all of these different ranges. So I like to go over this figure because although it also, it shows the levels of organization in biology, it also reflects kind of a good organization of the way our class is going to go. And so I always kind of like to start with that figure as we go through. The majority of the material that's in this chapter is going to be on the scientific method. And the scientific method is just a structured, organized, rational way to approach a question or a problem. And so what I've asked for you guys to do in your assignment is to think of some question, think of some problem that if you've ever been cooking in the kitchen you've thought of, or if you've ever been talking to your kids and they've asked you a why question that you never knew the answer to. If there's some way that you can start to get at what the answers to those questions are and do it following the scientific method, then that's a good way to kind of learn about what the scientific method is. And one of the things that we talk about as an outcome or competency of this course and an outcome of general education as a whole and as part of the scientific method is the idea of critical thinking. And so your book gives you this table that's kind of a guide to critical thinking. We talk about critical thinking a lot, but sometimes it's not always evident or apparent what it means to say critical thinking. We want our kids to think critically. We want to think critically. College is supposed to teach critical thinking, but what really is critical thinking? And so this is one section of the book that can help you kind of figure out what critical thinking means. And then another resource that we have is this website on Bloom's Taxonomy. I give you the link here in the PowerPoint. And then I'm going to have to pull it up separate. So I can push it out to you guys, I think. Oh, I don't want to draw on that. I thought I had the link in here for me to click on, so I just need to do this real quick. Sorry, I really thought that I had this ready for you guys. Okay, so this is going to, when I push out this link, it's going to open in a new window for you. If your pop-up blocker is on, it'll block it. But if not, it'll pop up in a new window. And then when you're finished with the window, you can either minimize it or close it. Hopefully. Yay, there it is. So this is a website put together by a couple of professors at Old Dominion University to show what we're talking about when we mean developing critical thinking skills. This is based on some educational research called Bloom's Taxonomy, done by a guy whose last name was Bloom and who named it after himself. And so it's based on the idea that critical thinking has to be developed in stages. And the very first stage of learning anything is going to be to learn facts. You have to learn basic facts about something before you can be really analytical or before you can do the critical thinking about it. So the very basic level is going to be to learn terminology, to learn facts, to learn structures, those kinds of things. And then you can memorize a word and not understand what it means. And so the next step is comprehension or understanding what that term means. Can you explain the idea or the concept? The next step is, can you apply the concept? Can you use that information that you've learned and apply it to a situation? The next level is analysis. Can you analyze? Can you make comparisons? Can you differentiate between two different things? A higher level is evaluating or synthesis. Can you put ideas together? Can you use an idea to justify something? And then ideally, can you take that information that you've learned and apply it in a totally new way, or can you create something new with that information? Can you take that information and create a new argument? Can you take that information and develop something from it? The thing I like about this website is it's very simple, but it gives you some examples of, if you were going to answer an essay question, these would be some of the action words that would start an essay question. Can you list something? Can you recall? Can you define something? That's going to be your first level. And then can you compare things? Can you differentiate between two different things? Comparing means pointing out the similarities. Contrasting and differentiating means pointing out the differences. Can you make that kind of analysis or that kind of comparison? And so I like this website because it kind of points out what we're talking about by the levels of critical thinking. And we're going to get a little more into this next week because I'm going to give you some more concrete examples about some topics that we're actually learning about. So when you're done with that website, you can either minimize it or you can close it entirely. If you ever want to go back to it, the link is here on this slide in the PowerPoint, so you'll be able to get to it. I wanted to make sure that you guys had both the link as well as saw the site. So in Chapter 2, we're getting into some basic ideas of biochemistry. I just saw Robin's question. Sorry, Robin. She's asking if you need to give me the topic beforehand for your scientific method assignment. You will not need to do that. I know a lot of people sometimes have an idea, and then as they try to develop the assignment, they get a different idea or they want to go a different direction. So I don't require that you give me the topic ahead of time. If you have any questions or if you want to email me and say, am I on the right track? I've had students do that before. And most of the time my answer to them is yes. Keep going with that. That's great. So you can, if you want to, email me and we can discuss it, but you are not required to do that. So our very first figure that we looked at, figure 1, started with atoms, and that's where we're going to start with our discussion. That's where Chapter 2 starts. Chapter 2 starts by talking about the structure of atoms. And so this is a figure from your book in Chapter 2 that shows you the structure of an atom. There's 3 particles, subatomic particles, that make up an atom. They are protons and neutrons and electrons. Protons are positively charged, so a lot of times we'll abbreviate them P with a little plus to show you that they're protons and they're positively charged. Electrons are negatively charged, so a lot of times we abbreviate them E with a little minus sign. And neutrons don't have a charge, so we sometimes say they're neutral. So sometimes we just abbreviate them N, or N with a 0 as a superscript to show you that there's no charge there that we're talking about. And the arrangement of these particles is that the protons and the neutrons are in the center in an area that we call the nucleus. And the electrons circulate around the nucleus in spaces that are called electron shells. And so a lot of what we're getting into is going to sound like chemistry. A lot of what we're getting into is going to sound like if you took a chemistry class in high school or if you've taken a chemistry class in college. It's going to use a lot of terms and concepts. And so for Chapter 2, it's going to be very similar to some of that material. But it forms the basis of some of the other things that we're going to talk about. And so we're only going to focus on the aspects of it that apply to biology. So it will be kind of a biochemistry kind of chapter. But that's one of the reasons I wanted to start with that first figure, is to show how it fits into all the things that we're going to be learning. Because a lot of times when we get into this chapter, people have the tendency to ask themselves, why am I learning this if this is a biology class? Which is a very legitimate question, which is why I'm trying to answer it for you. So the electrons circulate around the nucleus in a series of energy levels, or what we call electron shells. And so I showed you that figure just now to kind of give you a visual idea of what we mean when we're talking about these electron shells. The electron shells have a maximum number of electrons they can hold. The first electron shell can hold up to 2 electrons. The second electron shell can hold up to 8 electrons. And the third electron shell can hold up to 8 electrons. Now, there are bigger and bigger electron shells beyond that. And if you were taking a true chemistry class or like a physical or physics class, you might talk about 16, 32, 64. There are larger energy levels or larger electron shells that can accommodate more electrons. But for the purposes of the atoms that we'll talk about in this class, this is as far as we need to go. And so I have a couple of other principles on here, and we'll come back to this slide when we need them. But one of the things that I've told you here is that atoms are most stable when their outer electron shell is full. Not stable like crazy ex-girlfriend stable, but stable as far as reactivity, or what reactions that atom can undergo. And then another idea that I've told you is that opposite charges are attracted to one another, and things with the same charge repel each other or push against each other. This opposites attract principle is found quite a bit in nature, and we'll see it several times as we go through some of this chapter. So a figure that kind of demonstrates what I was pointing out in that previous slide is this figure. It's figure 2.3. And they show you the first and second and third electron shells. We show them to you as kind of circles around the nucleus, but atoms are three-dimensional objects. So these are actually kind of spheres or shells around the nucleus. That first shell can hold up to 2 electrons. And when its outer electron shell is full, we say that element is stable. It doesn't usually undergo any kinds of reactions. So helium is very stable. And that's good because we put helium gas into balloons and give them to children. And if it was very reactive or it had the potential to explode or to react, it probably would not be safe to put helium in balloons and give them to people. So we know that helium must be very stable. It must be very safe because we put it in balloons and give it to people. And now we know that's because its outer electron shell is full, and that makes it very stable. The second shell can hold up to 8 electrons, and the third shell can hold up to 8 electrons. So, for example, sodium that has 11 electrons has 1 electron in its outer electron shell. Chlorine that has 17 electrons has 7 electrons in its outer electron shell. So how do we know how many electrons an atom is supposed to have? It's based on something that we call the atomic number or the atom number. We give each atom an atom number or an atomic number, and it corresponds to the number of protons in the nucleus. But then down here I tell you that an atom is electrically neutral. Its positive charges has to equal its negative charges for it to overall be neutral. They would have to cancel each other out. So therefore, the number of protons has to equal the number of electrons in an atom. So we can use this atomic number that defines an atom to tell us both how many protons are there, as well as to help us figure out how many electrons are there. Because if it's an atom that we're talking about, those numbers will be equal. In a few minutes, we're going to talk about ions. And in ions, those numbers are not necessarily equal. But in an atom, those numbers are going to be equal. So we've talked a little bit about the structure of the atom. They're made up of subatomic particles called protons, neutrons, and electrons. Protons and neutrons are in the nucleus. The number of protons determines what atom you're looking at. The electrons circulate around the nucleus in these electron shells. The number is determined by that atomic number because it'll be equal to the number of protons in an atom. 2 can go in the first shell. The second shell can hold up to 8, and the third shell can hold up to 8 more. And so we can join atoms together to make molecules. We can hold them together by different chemical bonds. Atoms try to form chemical bonds to try to complete their outer electron shell because they're most stable when their outer electron shell is full. And there are 3 types of chemical bonds that we're going to talk about. The strongest one we're going to talk about are covalent bonds. The weakest 2 are ionic and hydrogen bonds. And hydrogen bonds are the weakest of those. Now, this slide, I started off with this sentence. The outermost electron shell determines the reactivity of the element, or what reactions it can undergo. Because the atom is trying to make itself stable, it's trying to fill up its outer electron shell. Wherever there's spaces in that outer electron shell, that atom is going to try to fill in those spaces with electrons if it can, to make itself more stable. and it undergoes reactions to try to do that, to form bonds to self-stable. So that's what I'm going to go through and try to explain to you at this point. So I tell you here the atomic number of sodium is 11. If you ever need, if you're taking a test or anything like that and you ever needed to know an atomic number, you don't have to memorize those. Those will be given to you. So for example, for this question right here, if you in real life ever need to know an atomic number, you can find that in the periodic table. The periodic table lists all the elements that we've identified to date and all kinds of information about them, but it includes their atomic number. So that's something that you'll be able to reference. You won't have to memorize atomic numbers. If you needed it to answer a question, it would be given to you. So here I tell you the atomic number of sodium is 11. Can we determine what the structure of this sodium atom is? So if its atomic number is 11, that means it has 11 protons. And those protons are going to be in the center of the atom, in the nucleus of the atom. If it's an atom, it's electrically neutral. So the number of pluses will equal the number of minuses. The number of protons will equal the number of electrons. So it will also have 11 electrons. And they will be arranged in these electron shells that circulate around the nucleus. The first one can hold up to 2 electrons. The second shell can hold up to 8 electrons. 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have one more. In that outer electron shell of sodium, there's only one electron. Circulating in this one electron shell all by itself, way far away from the nucleus. Sodium is very reactive. Sometime when you have a chance, get on YouTube and search for a video of elemental sodium. You will see people standing behind plexiglass shields, wearing glasses, holding it in tongs. If you drop it in water, it gives off a lot of light and a lot of heat in this very volatile reaction. Sodium is very reactive, has a lot of spaces in that outer electron shell. It is not very stable at all. We definitely do not put sodium in balloons and give them to people. That would be very dangerous. In fact, they don't let you do a lot with elemental sodium in classrooms anymore because you can watch it on videos and see what happens. Sodium is very, very reactive because of all that space in that outer electron shell. And so the next slide I give you says draw a chlorine atom, and we're going to do the same thing. We'll use a different color. Atomic number of chlorine is 17, so it will have 17 protons. And if it is an atom, it will be electrically neutral. It will also have 17 electrons, and they will be in 3 electron shells. 2 can go in the first. Up to 8 can go in the second. That's a total of 10. Now we can put 7. Put the rest of them in this outer electron shell for a total of 7. And so chlorine is got one empty space, so it can take 1 electron in order to be stable. So if you want some better images of what the sodium ion and the chloride, or the sodium atom and the chloride atom structures are, they can also be found in Figure 2.3 on page 22 in your book. They're both in C because they both use that third shell. And so they show you the structure of sodium and they show you the structure of chlorine. And then in Figure 2.4 on page 23, which is this figure right here, they show you that if sodium were to lose its electron out of that outer electron shell, that would drop it back to the second electron shell, which is full, and that makes sodium much more stable. Sodium is much more stable as an ion, having lost that electron, than it is as an atom. And so sodium can lose that electron and become more stable. Chlorine can take on that electron and fill its outer electron shell, and that makes chlorine much more stable. Now, we've not done anything to the nucleus, so we've not changed the atomic number, so sodium is still sodium, still has 11 protons in its nucleus. Chlorine is still chlorine, it still has 17 protons in its nucleus. All we've done is subtract or add an electron from the outer electron shell. We've not affected the nucleus, so we've not affected the identity. All we've done is gained or lost an electron to make an ion. Since sodium has lost an electron, it now has one less electron than proton, so it ends up having a little bit of a positive charge, and so we can write its chemical name with a plus to show you that it's a sodium ion, that it's a positive ion. Positive ions are sometimes called cations. And then for chlorine, it has gained an electron, so it has an extra electron, so it has an extra negative charge, so we can write chlorine's chemical formula with a minus sign. And it's a negative ion, and the term for that is anion. I always remember because it has an extra N for negative. And then somebody told me one time for cation that the T reminded them of a plus. So those are some hints. So ions are basically atoms that have gained or lost an electron. Again, we're not doing anything to the nucleus. We're only gaining or losing electrons in the outer electron shell. And they do this to try to fill that outer electron shell to be stable. And then the actual bond forms because of the opposites attract principle. The negative ion and the positive ion are attracted to each other, and that's what forms sodium chloride crystals, which we know as salt, as table salt. So the next kind of bond we're going to talk about is a covalent bond. So here again, the atoms are trying to get as many electrons in that outer electron shell as they can to try to make that outer electron shell full because it makes them stable. And so here we're going to have sharing of electrons that creates the bond. That's what makes covalent bonds so strong, is that this is actually sharing of electrons between two atoms. In an ionic bond, one atom gave its electron to the other and created two ions. Here, we're just going to share an electron between two atoms. And an example of that I always use is to look at water. So we can draw the structure of oxygen. Oxygen's atomic number is 8. So it'll have 8 protons in its nucleus. Oh, look. This is much better. So 2 electrons can go in its inner electron shell, and then 6 can go in the next. So that's going to leave 2 empty spaces. And I can do these red circles to show where the spaces are. So water is an oxygen atom and 2 hydrogen atoms. Hydrogen's atomic number is 1, so it has 1 proton in its nucleus. And it has 1 electron that circulates in its electron shell. And there's 2 of those in a water molecule. So here's an oxygen atom and 2 hydrogen atoms. And to form a water molecule, to form H2O, what can happen is that we can have sharing of a pair of electrons between the hydrogen and the oxygen. And if we share these 2 atoms, these 2 electrons between the atoms, then at least part of the time there can be 8 electrons around the oxygen. And at least part of the time there can be 2 electrons around each hydrogen atom. Your book shows this on page 25, kind of toward the top of page 25. And so by sharing electrons, all of these atoms can become stable, and they're held together in a molecule that we call a water molecule. Now, one of the things that's unique about oxygen is it has a property. It's what we call electronegative. And that means that it didn't learn to play fair. When it went to atom nursery school, it did not learn to share its electrons. And so it tries to hold on to electrons more tightly. It doesn't share those electrons. And so up here, I tell you that covalent bonds can be polar or nonpolar. A polar covalent bond is unequal sharing of electrons. And that's going to happen here in this water molecule. And polar covalent bonds set up the conditions for our next bond that we're going to talk about, which is hydrogen bonds. So there's a couple of animations on bonds and covalent bonds. So polar covalent bonds happen quite a bit when we have hydrogen covalently bonded to some other atom that's very electronegative. So the electronegative piece means that it holds on to the electrons more than the other atom. And that other atom is usually hydrogen. And so remember, polar means unequal sharing of electrons. So if we have this electronegative element that holds on to the electrons, that sharing is going to be unequal. And that is going to set up hydrogen bonds. So actually what I want to show you, so because the oxygen kind of holds on a little more tightly to the electrons, it has a slight negative charge. Because the hydrogens don't hold on to the electrons as tightly, they have a slight positive charge. Now, overall, this molecule is neutral. Overall, we will have the same number of electrons and protons. But we're not talking about number, we're kind of talking about the distribution. And they will be more likely to be found around oxygen than around either of the hydrogen atoms. And so, again, we have the opposites attract principle that tells us that the partial positive of a hydrogen is going to be attracted to the partial negative of an oxygen on another molecule, and that attraction is the hydrogen bond. And so hydrogen bonds actually form between molecules of water here, between the hydrogen of one and the oxygen of the other. Now, the hydrogen bond is what gives water a lot of its properties. Its ability to hold heat, its ability to dissolve things. It gives it a property called surface tension. If you've ever done the experiment with your friends or your kids where you fill up a glass of water and it looks full, and then if you add some drops of water very gently, you can actually get the surface of the water to bulge up above the edges of the glass. That's surface tension. Now, eventually you add so much water that the weight of the water overcomes the surface tension or the strength of the hydrogen bond. But it's hydrogen bonds that are holding those water molecules so that you can add more water than the glass would actually hold. You can add more than what the volume of the glass is, and you can see that water kind of bulge up, and the hydrogen bonds are what's keeping it together. Now, another thing that this aspect of water helps with is dissolving things. And so, if you remember, our sodium ion was a positive ion or a cation. And so the negative part, the slightly negative part of all of these water molecules is attracted to the positive sodium ion. And the chloride ion was an anion or a negative ion, and the more positive part of the hydrogens of this water molecule are attracted to it. And it actually surrounds it with a sphere of water that we sometimes call a hydration sphere or sphere of hydration. And this is why salt dissolves so readily in water. Table salt, as soon as you put it in water, it dissolves and it breaks down because this is what's happening. But this is also why we put salt on ice to help melt ice, because the salt can disrupt the hydrogen bonds in between water molecules that hold the ice together. The salt can disrupt those hydrogen bonds and can melt the ice. Are there questions on any of that stuff so far? I kind of took, there is a slide that gives you some summary of these bonds that we've talked about. We kind of looked at the structure of the atom, and the structure of the atom kind of lends itself to the way that these three bonds form. And so that all kind of fits together. Atoms and molecules and chemical bonds all kind of fit together there. Okay, the other thing that I kind of want to go through a little bit with you is a little bit of discussion on organic compounds. There's basically 4 classes of organic compounds that your chapter ends up talking about: carbohydrates, lipids, proteins, and nucleic acids. And we can look at the subunits of each of these. Carbohydrates are made up of single sugar subunits. We string together a bunch of single sugar subunits, we get these carbohydrates. Lipids are made up of a lot of different subunits, but fatty acids are one of them. Proteins are made up of amino acids. And nucleic acids are made up of a subunit called nucleotides. And your book takes you through each one of those. And so all of these subunits can be put together to make up these larger chains, or the larger chains can be broken down into these individual subunits. And when we put the subunits together, that's a condensation reaction or a synthesis reaction that's called dehydration synthesis. And your book talks about that. And then when we break them down, that reaction is called hydrolysis. It's a breakdown reaction. So your discussion board post is going to be to find some sort of molecule that you're interested in that's in one of these 4 categories. Tell us which category it's in and if there's anything unique about its structure or its membership in that category. So your book talks a lot about proteins and protein folding and their 3-dimensional structure. So maybe your protein that you're interested in is something like insulin. Insulin is a protein, and so you can talk about how insulin has to be folded properly in order to do whatever it does. You'll have to explain that in your post. Maybe your molecule that you're interested in is one of the sugars or one of the starches, and you can talk about why it's important or why its structure is related to what it talks about in your book. So I wanted to go through a little bit about this with the subunits and the organic compounds, since that's going to relate to what's in your discussion board post this week. So what questions do you guys have? You can feel free to type in anything in the chat box if you want to, if you don't have a microphone. Is there any other part of this chapter that you thought was confusing or that you want me to go over with the explanation? Okay, well, I will, the archive will be made available as soon as I push my little red button at the top of my thing. So if you guys want to go back through and look at anything, you can feel free to. or you have the PowerPoint that you can go through. If any questions do come up, you can feel free to post them on the discussion board. There's an area on the discussion board for questions, and you can post anonymously. So if you have a question that you think other people might have also, and you just want to post it anonymously and so that that question can get answered, then you have the option of doing that as well. So please let me know if you have any questions or anything as you're working through some of the material, and I will get them answered if I can.